Data agents are supposed to automate data science. They plan, write code, execute in sandboxed environments, and return insights with minimal human intervention. But when you push these agents into real-world data workflows, they consistently underperform. The problem isn't just that the underlying models are weak. It's that our evaluation frameworks are fundamentally broken. Most existing benchmarks rely on small, synthetic datasets, aggregate pass-fail scores, and coarse task categories. They hide step-level failures, ignore real-world data scale and schema complexity, and provide zero granularity on why an agent failed. If you want to actually improve data agents, you need a benchmark that mirrors industrial-grade data science, tracks fine-grained skill application, and exposes exactly where and why reasoning chains break. That gap is exactly what AgenticDataBench addresses. It's a comprehensive, open-sourced evaluation framework built around 344 realistic data science tasks, spanning 27.3 gigabytes of data across 15 distinct domains. But the real innovation isn't just the volume. It's the methodology. Let's break down how they built it, how they evaluate agents, and what the empirical results actually tell us about the current state of LLM-driven data science. The foundation of the benchmark is a hierarchical data science skill framework. Instead of treating tasks as monolithic prompts, the authors decomposed data science workflows into 433 distinct, reusable operational patterns. These skills are organized into 7 exclusive categories that map directly to the data science pipeline: data format handling, data preprocessing, data manipulation, data analysis, data modeling, data visualization, and cross-stage skills like environment management, error handling, and SQL optimization. Extracting these skills wasn't a manual tagging exercise. It's a fully automated, multi-stage pipeline. First, they pulled 6,510 high-quality data science solutions from Stack Overflow and used LLMs to decompose each solution into stepwise rationales. That initial extraction produced nearly 30,000 low-level skill descriptions, but they were plagued by redundancy, entanglement, and loose definitions. To fix this, they applied a hierarchical clustering pipeline. They encoded the stepwise descriptions using Qwen 3 embedding, reduced dimensionality with UMAP to preserve local manifold structure, and applied Gaussian mixture models for soft clustering. Since embeddings alone can't reliably capture high-level skill boundaries, they fed each cluster back into an LLM to split it into coherent subclusters aligned with actual data science operations. They then used DBSCAN with a strict distance threshold to detect and merge synonymous skills, keeping the shortest description as the canonical representation. Finally, they recursively summarized the resulting skill nodes, reclustered them until they hit a predefined threshold, and had domain experts validate the hierarchy. The result is a compact, non-entangled tree of 433 skills that actually reflect how data science is practiced. Once you have a reliable skill taxonomy, you need tasks that exercise them. The benchmark draws from 2 sources: real-world business tasks and systematically generated public dataset tasks. For the real-world component, they worked with a leading fintech company to curate 600 anonymized production tasks. Since many of these share identical operational structures with only minor parameter or dataset variations, they formulated task selection as a maximum coverage problem. Selecting a subset of tasks under a fixed budget to maximize skill coverage is NP-hard, but because the coverage function is submodular, they applied a greedy approximation algorithm that iteratively picks the task covering the largest number of previously uncovered skills. This yielded 102 highly diverse, skill-annotated business tasks. For the remaining 242 tasks, they needed to ensure comprehensive skill coverage across public datasets without relying on human annotation at scale. They constructed a skill graph where nodes represent skills and edges represent consecutive skill usage observed in real solutions, weighted by frequency. To generate a new task, they sample a random path through this graph, which dictates the skill composition. They then prepare structured data profiles for target datasets, including basic metadata, format-specific structures like column types and missing value patterns, and cross-file join relationships identified via both programmatic attribute matching and LLM-based semantic alignment. Using the sampled skill path and dataset profiles, they iteratively synthesize a solution workflow by prompting an LLM to insert each skill into the pipeline, verify step actionability, and enforce dependency coherence. Once the workflow is stable, they generate the task description and ground truth solution, which are then refined by experts to ensure solvability, conciseness, and verifiable answers. This entire pipeline required nearly 1,600 person-hours of expert curation and labeling. Now let's look at how they actually evaluate agents. The testbed runs inside isolated Docker containers with Bash, Python, and database execution capabilities. Each benchmark instance includes a task description, dataset, ground truth solution, annotated skill requirements, and a task-specific evaluation function. The evaluation supports 5 distinct scoring modes: exact and tolerant table matching, modeling-based metrics like normalized mean squared error, JSON key-value matching with numerical tolerance, chart matching that verifies both underlying data and plot configurations, and exact or fuzzy text matching. But the real diagnostic power comes from the skill-level analysis. After an agent finishes, the system compares its output to the ground truth, uses the annotated skills as candidate categories, and prompts an LLM to score each skill application. This reveals whether a failure came from a syntax error, a misapplied statistical test, or a breakdown in environment management. They ran this pipeline against 4 representative agent harnesses: DA agent, small agents, Claude Code, and Codex, paired with 3 state-of-the-art LLMs: Qwen 3, 5-397BA17B, Kimi K2, 5, and Claude Sonnet 4.6. The results expose several critical dynamics about the current landscape of data agents. First, general-purpose harnesses currently outperform data science-specific ones in raw accuracy. Codex and small agents consistently beat DA agent. This isn't because general-purpose agents are smarter, it's because they've had more engineering cycles. DA agent uses a lightweight design with a fixed memory window and lacks specialized components like data profiling tools or domain-specific skill injection. The performance gap highlights a trade-off. Specialized harnesses are more efficient but less robust, while general-purpose harnesses absorb complexity at the cost of higher token consumption. Second, LLM and harness compatibility is a massive, often overlooked factor. The best-performing model changes depending on the orchestrator. Claude 4.6 dominates within DA agent and Claude Code, largely because of its superior coding precision and ability to follow complex instruction formatting without syntax drift. Qwen 3, 5 performs best with small agents, which uses a notebook-based execution model that shares loaded data across steps. Kimi K2, 5 excels in Codex, which aggressively explores multiple solution paths and benefits from Kimi's concurrent execution style. When you mismatch them, like running Claude 4.6 through Codex, you see context overflow issues and premature termination, because the model doesn't align with the harness's auto-compaction and memory management patterns. Third, cost and performance don't scale linearly. Claude 4.6 delivers high accuracy, but incurs substantially higher token costs, especially in output-heavy harnesses. Qwen 3, 5 paired with lightweight orchestrators like small agents or DA agent offers the most favorable cost-performance ratio. The data shows that if you're optimizing for production efficiency, you're better off with an open-weight model and a lean harness than a premium model with heavy orchestration. When you drill down to the skill level, the failure patterns become stark. Data analysis consistently accounts for the largest share of agent failures, even though it's not always the most frequently invoked skill category. This is where agents struggle with data validation, statistical calculation, and summarization, and those errors frequently propagate downstream. Cross-stage skills, particularly command-line operations and dependency management, also expose significant weaknesses. Agents that rely on general-purpose harnesses often generate invalid shell commands or fail to recover from missing packages, which directly explains poor performance in domains like tourism that require heavy file automation and environment setup. Domain-specific failure modes also diverge sharply based on data characteristics. In marketing tasks, which involve large single files around 1 GB, agents frequently hit global step limits or single-step timeouts because they reload data repeatedly instead of maintaining state. Healthcare tasks with heterogeneous formats like ARFF files trigger the highest self-repair failure rates as parsers break on non-standard schemas. Meanwhile, loan model tasks, despite having simple 2-table structures, suffer the most from data modeling failures because agents struggle with complex feature derivation, high-dimensional training, and proper hyperparameter tuning. When the per-step timeout is increased to debug timeout failures, scores don't improve. The agents just loop longer on flawed reasoning trajectories, confirming that the bottleneck isn't compute time, it's architectural alignment. The takeaway is clear. Evaluating data agents with aggregate scores is obsolete. You need fine-grained, skill-level diagnostics to understand where pipelines break, how harnesses interact with model capabilities, and which domains require specialized tooling. AgenticDataBench provides exactly that infrastructure. It moves us from asking whether an agent can solve a task to understanding how it solves it, where it fails, and how to systematically improve it. The full testbed, skill hierarchy, and evaluation pipeline are open source. If you're building data agents, designing evaluation frameworks, or pushing LLMs into real-world analytical workflows, this benchmark gives you the granularity you've been missing. The research is available on arXiv, and the codebase is public. I'll leave links in the description. If you want to dive into the skill extraction algorithms, the greedy coverage optimization, or the full empirical breakdown, the paper has the complete methodology. Data science automation isn't going away. But until we measure it with the same rigor we apply to model training, we'll keep hitting the same walls. AgenticDataBench changes how we track progress. It's a necessary step toward reliable, skill-centered data agents. Thanks for watching, and I'll see you in the next one.